So thank you. This is an opportunity for me to greet all the volcanological community. My project is on Magma ascent dynamics and volcanic erosion style modeling using a method combining fluid mechanics laws and thermodynamics principles. So volcanic erosion are between the most old phenomena that the Earth know until today. So we would like to address this question. Why do we continue to study this phenomena? So the complexity of the processes associated and the tree they represent make them a real actual problem. So many works combining different techniques has been done in the field and many others remain undue. I was studying for use the fluid mechanics and thermodynamics law to study the motion of magma during the ascent. To better construct the study, we use these outlines. For the origin of magma, many processes can allow magma to form and we have plate tectonics, which are the theory of plate motion. The descent of plates stirs up the mantle, bringing over a current of warmer material from the depth, facilitating melting by decompression and resulting in magma generation. In other way, we have the role of water. But water play an important role. So the water introduced into the mantle wedge above the subduction zones lowers the melting point of mantle rock, facilitating magma generation and volcanism at the surface. And last, we have the hotspot. Unusual geochemical signature in the basaltic hotspot lavas suggests a magma source deeper in the mantle than the mad ocean ridge. Magma can erupt to the surface using different ways, and the current way used is a dike. So dikes are formed by fracturing the hotspot due to magma injection. The dike phenomena has been described by Kachman and others, and it is represented in this figure. Zeymar has proposed an approximation of the phenomena here, and for this study, we use a physical modeling approximation of the ascent conjugate that is represented here by this figure. Yes. The other way that magma can erupt to the surface is the cylindrical conduit. This theory supposes that magma chambers is located underneath the volcano edifice in the upper crust. For physical modeling, we need to specify some magma physical properties. So we know that magma temperature is high, and this has an effect on the wet forces. Therefore, magma wet forces is affected by temperature of magma and temperature of magma at the source. Magma is a viscous fluid, and this will affect the motion of the magma of his motion during the ascent. Therefore, we take into account the frictional forces which is described by this relation, and where U is a viscosity and K the permeability parameter. Magma can also be described as a Newtonian fluid. And it is important to know that Newtonian fluid is a fluid that viscosity is constant for different rates of shear and doesn't change with time. Pressure in magma is an important factor. Therefore, the forces due to pressure can be described by this relation, where P is the pressure and dV the elemental volume. For the mathematical model, we use the physical modeling to constrain the mathematical model. So during the ascent of the magma, we know that a rate of magma that enter a closed surface is the same that we get out to the surface. So that's and according to the incompressibility of magma, we get the equation describing the conservation of mass in 2D modeling that is described by this relation. For the equation, the motion equation, we We got it using the conservation of momentum. So forces due to acceleration is equal to all the forces that affect magma motion. So which are the pressure forces, forces due to rheology, forces due to friction, due to viscosity, and forces due to wet forces. And the last equation is obtained using the first principle of thermodynamics, and it is the equation of energy conservation, which is described by this relation. After resolution, we got the expression of u, which is the velocity, theta, which is the temperature. So we can see that those expressions are a function of a combination of a hyperbolic function. That means that velocity and temperature increase or decrease exponentially during the ascent. For parameter description, G used here is a reduced Kirchhoff number, R the Reynolds number, sigma the permeability parameter, and N the perturbation parameter. We have used the Python environment to obtain some result. And the figure 1 represents the effect of fragmentation on the velocity during the ascent. We can see that when rates of fragmentation increase in the conduit, magma velocity also increase. In the figure 2, we have the effect of buoyancy on the magma velocity. When buoyancy increase in the conduit, magma velocity also increase. In this slide, we have the simulation of magma temperature. In the figure 1, we have the effect of perturbation on the temperature. When a perturbation increase, magma temperature also increase. In the figure 2, when the rate of fragmentation increase, magma temperature decrease. And in the last figure, when buoyancy increase in the conduit, magma temperature also increase. In conclusion, this model can well describe the motion of magma within conduit. The model can also be used to forecast erosion style, physical property of the earth, internal structure. Magma chambers, magma reservoir are well known in advance. With a well scaling of the perturbation parameter, the model can describe the formation of magma chambers. As suggestion, a numerical method modeling using a suitable numerical method needs to be done to validate the model, and other physical properties need to be added for a more accurate study.